as the globe buzzes with excitement over the all-clear signal for 3 Atlas, history's third interstellar voyager, a more disturbing development lurks in the background. And we've only just caught on. A comet bursting with flares is drifting nearer to our planet's path than we'd ever want. It evaded our scopes until the sun's glow betrayed its position. Come October 20th, 2025, merely 8 days away, it'll hit its nearest point to Earth. What implications does that hold for those of us down here? Is this the true peril? Stick around to the finish, and I'll reveal why the actual danger isn't the comet grabbing all the headlines, but the one that nearly escaped our notice entirely. If these enigmas grip you like they do me, smash that like button and subscribe to catch every live update as events play out. Leave a comment sharing your location, the local time, and if you think we're hearing the whole story on these game-changing finds. To boost this community, spread the word by posting this clip on X, Facebook, Reddit, or your personal chats. You folks make it possible for us to pursue tales like this. Thanks for the support. Let's dive into part 1, tackling the headline buzz straight away. The chatter's all about 3 Atlas. News outlets label it enigmatic. Social media explodes with speculations, while experts twist themselves into knots to calm fears that it's harmless. They're spot on. This cosmic drifter from outside our solar system will sail by Earth at a safe 1.8 astronomical units, about 167 million kilometers. NASA's been crystal clear, zero risk. Its path keeps a wide berth, like a starry tourist that zips through and fades into the cosmos. So what's fueling the fixation? It's from another realm. The term interstellar sparks that wonder, blinding us to the basics. We adore the alien guest knocking at our gate. We overlook the intruder already inside. As eyes fixate on 3 Atlas, a different body sneaks into our cosmic turf. Meet Comet C/2025 R2, nicknamed Swan for the detection tool that uncovered it, drawing ever nearer. On October 20th, 2025, 8 days out, it'll make its tightest pass by Earth. Forget $1.80 or even one. Try 0.2606 astronomical units, around 39 million kilometers. That's nearer than you'd imagine. Closer than we'd tolerate for unannounced visitors. Let me paint the picture of this beast. R2 popped up in late September 2025, spotted by hobbyist astronomer Vladimir Bezugi, sifting through solar wind readings from the SOHO probe's onboard gear. No eyepiece involved. He tracked hydrogen flares shimmering in UV rays. That's an unusual comet hunt. Typically, Earthbound optical scans rake the heavens for dim specks bouncing back sunlight. Yet R2 dodged them. It lurked in the sun's blinding halo, too tightly aligned angularly for ground scopes to pick out. This quirk's dubbed the Hulacek or Holik blind spot phenomenon. Items there are spectral, present, yet undetectable till they break free. R2 broke free post-perihelion, its sun-closest mark on September 12, 2025. When we finally nailed it down, it was outbound, barreling our direction. That perihelion sat at roughly 0.5 Australian dollars, some 75 million kilometers from the sun, near enough to bake away ices, spark eruptions, and rattle its frame. And erupt it did. Late September brought reports of a sharp surge in brightness. The comet spiked to magnitude 5.9 or 5.6 per varying accounts. Its coma, that hazy envelope of vapor and grit around the core, ballooned. Images captured a green-tinged aura, the telltale glow from diatomic carbon and CN radicals lit by solar UV. The tail spanned several sky degrees, catchable with binos if you pinpointed it. But here's the kicker. The core's dimensions remain a mystery. Its spin? Unknown. Has it cracked, or might it? Comets are fickle monsters. They drop nuggets, break apart, hurl rubble streams across their routes. Should R2 fragment, those bits would veer off the main line a touch. They'd fan outward. They'd create a swarm risking overlap with our orbital track. The minimum orbit intersection distance, or MOID, linking R2 to Earth clocks in at about 0.048 AU, around 7 million kilometers. On a stellar scale, that's razor thin. The line between secure and potentially dicey hinges on what unfolds. I'm not claiming R2 will slam into us. Projections insist it won't. But the core issue is our failure to detect it sooner, exposing the genuine hazard. Our vigilant network shines for targets in optimal sky zones at ideal. The key to spotting these things lies in catching their glow precisely when it peaks. Yet if something ducks behind the sun's intense radiance, approaches from an odd direction, or flares up right after we've glanced elsewhere, it slips right by. That's exactly what happened with our two. We didn't notice it until it was almost right upon us. How many more have we overlooked completely? This isn't cause for alarm. Freaking out achieves nothing. Instead, it's a call to focus on the threats that typically evade detection. It's about understanding that the most alarming dangers aren't the flashy stories dominating the news. They're the stealthy ones that only appear when it's far too late to react. The hype around 3 Atlas is just a diversion. It's like the magician's flourish drawing your eye while the real sleight occurs out of sight. R2 represents that hidden maneuver. So, let's get to the plan. We'll start by breaking down the 3-eyed Atlas misdirection and explaining why it's no real threat. Next, we'll delve into all the details we have on R2, plus the gaps in our knowledge. We'll examine potential hazard paths, the vapor trails, the debris pieces, the clusters of meteoroids. We'll stack this up against previous close calls that we scarcely detected, threats that evaded our safeguards with mere days or even hours of advance notice. Finally, we'll cover what to monitor yourself, what to push for from the organizations tasked with tracking these risks, and the fallout when early warning networks break down, which they do far more frequently than most realize. And remember, breakdowns mean the intruder that gets through often isn't the one you had your sights on. Part 2. The mechanics of its discovery. Why did Swan pick it up when Earth-based scans missed it? Typically, comets get flagged through visual sweeps of the sky. Telescopes sweep the darkness for dim specks that shift position relative to the fixed stars. Those specks intensify as they near the sun. Their frozen surfaces turn to gas, sprouting tails behind them. Humanity has relied on this approach for ages. It's dependable, until it isn't. Comet C/2025 R2 evaded optical detection entirely. Instead, it was unveiled by a hydrogen emission sensor on a satellite circling the sun. That device, known as SWAN, for solar wind anisotropies, forms part of the SOHO mission, the Solar and Heliospheric Observatory, which lifted off in 1995. SWAN's purpose is to map solar wind patterns by capturing Lyman alpha hydrogen emissions in the ultraviolet range. Hydrogen emits light at 121.6 nanometers, a wavelength hidden from naked eyes but vivid in UV. As comets sublimate ice into water vapor, that vapor splits into hydrogen and oxygen. The hydrogen expands into a vast envelope surrounding the comet, dwarfing the observable dusty head. From tens of millions of kilometers distant, SWAN can detect that envelope even when standard telescopes detect zilch. This isn't some fresh technique. Throughout its service, SOHO/SWAN has uncovered thousands of comets. The majority are tiny sun-skimming fragments that dive into the sun's corona and disintegrate. R2, however, isn't a sun grazer. It's an intruder from the solar system's fringes, probably the Oort cloud, swinging in for a tight solar flyby before retreating outward. What kept it hidden from terrestrial observers was its location. It hugged too near the sun on the celestial dome. The angle was minuscule. Ground telescopes can't stare straight at the sun without frying their sensors. Encircling the sun is a forbidden region, a veil of obscurity where targets effectively disappear. Experts dub it the Hill sphere effect or the Hoyle blind zone, based on the pioneer you favor. The concept remains identical. Anything there becomes spectral, undetectable. R2 navigated its closest solar approach within that shroud. It arced around the sun on September 12, 2025, at about 0.5 Australian dollars, roughly 75 million kilometers out. For weeks prior and following, it stayed out of optical reach. Only after breaking free from the solar dazzle did it become visible, already post-perihelion and angling toward our planet's vicinity. That's when amateur astronomer Vladimir Bezuki sifted through SWAN's archived UV images, hunting for the signature hydrogen shimmer. He spotted a drifting patch, a hazy formation that migrated across frames. He marked it for review. Peers verified it. Visual backups confirmed the find. The comet existed, but precious weeks of tracking had vanished. We lacked intel on its pre-close approach actions. No records of its brightening rate, orbital shifts, or early signs of breakup. Late spotting acts as a harsh sieve. Visual patrols face brightness thresholds, patchy sky mapping, cloudy disruptions, and solar glare barriers. UV hydrogen detectors like SWAN offer contrasting strengths and weaknesses. They snag comets that evade optical gear, yet they're built for niche tasks, not full-sky patrols. Precision instruments excel at specific catches. The fallout from delayed alerts is grave. With scant data points, orbital predictions stay fuzzy. Refining paths demands extended viewing to gauge deviations and factor in extras like gas jets. R2 was we overlooked its late appearance. The trajectory remained unclear. Even after several weeks, uncertainties persist. We have a general sense of its path, but approximations fall short of exactness. In the realm of orbital dynamics, accuracy reigns supreme. Moreover, we failed to capture the initial outbursts. Comets frequently erupt close to perihelion, where intense solar warmth sparks the violent ejection of frozen gases. Should R2 have experienced such an event, it escaped our notice. We lack data on whether it released substantial debris during that phase. We remain ignorant of any potential fissures in its core. Its spin characteristics, influencing how it tumbles and twists amid uneven gas emissions, are equally unknown. All these details have slipped away. We're navigating without guidance as we forecast the actions of a body we only began monitoring midway through its performance. This shortfall doesn't stem from any single scientist's oversight. Rather, it highlights inherent weaknesses in our surveillance system. We've tailored our tools to detect specific celestial types in designated sky regions. Deviations from those norms lead to oversights. And those oversights can be total until a dedicated hobbyist, leveraging satellite data, spots a hydrogen emission in old records. How many additional comets have evaded us? How many are traversing the solar system at this very moment? Unseen simply because they occupy the incorrect spots at inopportune times. We have no answers, nor can we obtain them. That's the core issue. Moving on, let's examine R2's developments post-detection. The eruptions, the peculiarities, the compositional anomalies that elevate this comet beyond a mere frozen boulder. Part 3. R2's observed behaviors. I'll guide you through the sequence of events. On September 11, 2025, Vladimir Bezugi detected a drifting hydrogen emission in SWAN imagery. The body received the label C/2025 R2, with the R denoting the half-month of its unveiling and the 2 marking it as the second such find in that interval. Visual verification arrived swiftly. Terrestrial watchers aimed their scopes at the given position and beheld it, a hazy blot, a coma shimmering softly in the early morning darkness. The comet had traversed perihelion just prior, on September 12, at about 0.50,347 astronomical units from the Sun. That's proximity. Near enough to vaporize water ice, carbon dioxide, methane, ammonia, every volatile substance comets harbor. Near enough to ignite processes. And processes did ignite by late September. Spotters documented an abrupt surge in luminosity. The comet's visible brightness leaped. Certain assessments pegged it at magnitude 5.9, while others suggested 5.6. Remember, magnitude scales logarithmically, so minor shifts signal major gains in light output. The coma swelled. Snapshots revealed a verdant aura encircling the nucleus. That's the hallmark of diatomic carbon fluorescing under UV rays, a staple in cometary displays. Such carbon elements vaporize from the core, become charged by sunlight, and emit that eerie green. It appears otherworldly, yet it's pure chemical reaction. The tail exhibited imbalances. Certain photos captured streaks, slender streams of ejecta directed sunward. This points to focused venting, likely from dynamic openings on the nucleus's exterior. Comets aren't even. They're mosaics of frost and stone, with zones varying in volatile content. As the core turns, varied outlets face the sun, sparking intermittent flares. Consequently, the tail morphs, throbs, and occasionally divides into branches. R2 displayed every bit of this. Watchers also remarked on substantial dust holdover. Typically, sunlight's push disperses fine particles, crafting a sleek tail. Yet if particles prove coarse or adhesive, they trail sluggishly, forming a hazy veil that disperses gradually. R2 appears to generate plentiful coarse particles. This carries weight. Coarser particles imply the nucleus is ejecting slabs, perhaps shards, perhaps crustal flakes detaching from heat strain. Should those slabs prove sizable, they could persist as separate entities, each on its distinct course, potentially fanning a rubble zone through the void. A notably vivid photo surfaced on the Astronomy Picture of the Day site on September 18, 2025. It captured R2's emerald coma set against the dusky heavens, tail arching skyward from the veiled solar blaze. The comet hugged the horizon still, posing observation challenges, yet it stood out clearly. Sky photographers nabbed it, employing everything from binoculars to modest scopes. Accounts portrayed the tail spanning multiple degrees, a spectral band unfurling overhead. But consider this: forecasts for cometary brilliance are infamously fickle. Comets defy straightforward patterns. They flare up, they dim, they break apart. Their glow hinges on the extent of sublimating surface, tied to core dimensions, makeup, spin rate, and solar exposure. We offer informed estimates, but comets thrive on defying expectations. R2 stands forecasted to hit magnitude 4 in ideal conditions. Certain conditions could render it prominent enough for unaided viewing under clear night skies. More cautious forecasts indicate it might hover near magnitude 6, necessitating binoculars for observation. As of October 10, 2025, its brightness sits at roughly 6.7, teetering just shy of detectability by the bare eye. Further illumination hinges on potential future flares, though there's no certainty it will erupt again. The core stays indistinct. Observatories capture merely the coma, that luminous shroud of vapor and particles. The dense heart lurks within, concealed by its diminutive scale and subdued glow. Its dimensions remain unknown. Projections drawn from luminosity and outbursts point to perhaps a handful of kilometers across, yet that's mere speculation. Its form is a mystery. It might constitute a solitary body or a loose aggregation of chunks held by feeble gravity. Fragmentation could have already occurred. Some icy wanderers break apart subtly, dispersing fragments sans fanfare. Detection comes afterward, via detailed imaging of the coma revealing clustered densities, several cores. It's conjectural, yet intriguing. The flare in late September hints at volatile stores beneath the surface. Internal pressures mounted within the comet, culminating in a sudden expulsion. This might involve carbon monoxide frost vaporizing with force, or isolated water ice layers abruptly hit by solar rays. Perhaps a structural rupture allowed gases to escape. Regardless of the cause, it struck once. Recurrence is possible. Should it disintegrate at an inopportune moment, especially nearing our planet, the resulting rubble would form a diffuse swarm, one our path might intersect. Next up, we'll delve into the figures, precise orbital stats, separations, velocities, and configurations that gauge if this sparks interest or alarm. Part 4. Solid data and trajectory assessment. Here's the layout. Comet C/2025 R2 follows the Sun along an almost parabolic path. Its eccentricity measures 0.9993699, edging remarkably near unity without crossing it. Precisely one eccentricity denotes a parabola, an unbound arc where the body arrives from the void and departs similarly. A value just under 1 describes a vastly stretched oval, a loop spanning tens of millennia. For R2, the semi-major axis spans about 798 Australian dollars. Thus, its remotest orbital point, the aphelion, lies well past the Kuiper belt, penetrating the Oort cloud's depths. The cycle lasts an estimated 22,554 years. This visitor last graced the inner system in the late Paleolithic era, as early humans adorned cavern walls and pursued woolly giants. The path tilts at roughly 4.47 degrees. This represents the angle between the comet's plane and the ecliptic, Earth's orbital plane. Such a modest 4.47 degrees is shallow. Typical Oort cloud comets plunge in at sharp angles from varied directions. R2 aligns nearly coplanar with the planetary disk. This simplifies forecasting its course but heightens proximity risks as it lingers longer in the ecliptic zone where we circle. Perihelion, its sun-nearest spot, hit on September 12, 2025, at 0.50,347 Australian dollars, around 75 million kilometers, slipping inside Venus's track. There, radiant warmth scorches fiercely. Outer layers hit hundreds of degrees Celsius. Water frost turns to gas swiftly. Other ices liberate vapors. The core expels particles and fumes relentlessly. This phase ignites comets' glow, turning them dazzling yet precarious. Now, as R2 recedes sunward, its route intersects our orbital lane. On October 20th, 2025, it achieves minimal Earth distance, 0.26,065 Australian dollars, or about 38,925.17 kilometer. That's roughly 100 lunar distances. To us, it seems remote. Astronomically, it's a close shave. Crucial is the MOID, the minimal orbital intersection distance, the tiniest theoretical separation between our paths, ignoring timing, derived purely from geometry. For R2, it's around 0.048 AU, some 7 million kilometers. Imagine plotting both orbits and finding their nearest points, 7 million kilometers apart. That's the buffer. Misaligned timing could erase it entirely. But alignments favor us. Projections confirm October 20th separation at 39 million kilometers. The comet sweeps by harmlessly. Simulations affirm it, math backs it. NASA issues no alerts. No collision threats. So why persist? Because trajectories aren't flawless. They rely on sightings, and sightings carry errors. The greater the data points, though R2 offers the superior approach, it was only identified relatively recently. Our dataset includes far fewer measurements than ideal. The path remains fairly well-defined, yet not entirely pinned down. Minor disturbances, like non-gravitational effects from gas emissions, alterations in the comet's spin or material layout, could nudge the course just a bit. A deviation of several thousand kilometers may prove insignificant for the main body, but it carries major implications if fragments have broken away. Such pieces can veer apart. Should R2 break apart or divide into chunks, those segments would possess marginally varied speeds. Gradually, they disperse across the trajectory, creating a trail of rubble. Bigger chunks stray less, while tiny bits, dust particles, small rocks, can scatter extensively. Should Earth cross that rubble path, meteor sightings could surge, potentially escalating to a shower or even something more intense. As of October 10, 2025, its apparent magnitude stands at 6.7, fainter than forecasts indicated, though that's hardly unexpected. Comets dim as they recede from solar warmth. The key uncertainty lies in whether R2 will flare up once more. Such an event, a rapid surge in brilliance, would indicate fresh outbursts, perhaps splitting, maybe fresh volatile ejections, and that could alter the hazard assessment entirely. Picturing it aids understanding. Picture the Sun in the middle. Our planet's path forms a near-circular loop at about 150 million kilometers out. R2 traces an elongated oval, plunging in from the distant solar reaches, looping near the Sun, then retreating outward. These paths cross, but at different moments. The comet hits that crossing in October, while Earth follows months afterward. This separation in space and time keeps us secure, for now. Yet comets defy easy prediction. They don't adhere to fixed timetables. They sway, fracture, release debris, and those offshoots rarely mirror the core path precisely. They wander, fan out, and occasionally show up right when you think they're nowhere near. Shifting focus, let's examine the observational drama, the crowd-pleasing display, the diversions, and how news portrayals steer our focus. Section 5 covers the immediate spectacle, sightings, media buzz, and societal diversions. October's heavens are getting packed. Comet C/2025 R2 nears its Earth minimum around October 20th. But company arrives. Comet C/2025 A6, dubbed Lemon, is also gaining glow and appearing in northern skies simultaneously. Dual comets, both catchable by hobbyist stargazers, both hitting perihelion-like closeness mere days apart. It's a showstopper. Such alignments are uncommon. They draw eye skyward. Add the Orionid meteor display. The Orionids crest annually near October 20th to 21st as our world slices through Halley's comet residue. That's right, Halley, the legendary periodic visitor every 76 years. Even distant, its wake persists, a ribbon of icy grit along its route. Each October, Earth plows through, with bits colliding into air at 70 kilometers per second. They vaporize into luminous trails, shooting stars. Orionids usually yield 10 to 20 per hour at zenith, occasionally higher. No epic tempest, but steady as clockwork. Thus, on October 20th, 2025 evening, expect dual comets gracing the view alongside a topping meteor flow. The night sky buzzes, coverage explodes. Skywatchers deluge platforms with images. Broadcasters air tales of stellar splendor. Prime time for audience involvement. Yet it's also ripe for overlooking details. As folks chase the Aeronids, wait, Orionids, snap comet shots, and absorb awe-inspired reports on cosmic marvels, scant attention goes to tougher inquiries. Precisely how near does R2 get? What's the error range? Any splitting underway? Debris monitoring in place? What if surprises hit? The Washington Post highlighted the double comet affair, pointing out R2 and Lemon's accessibility via binoculars or modest scopes. They stressed the uniqueness, the allure, the thrill of twin tails. Proximity got downplayed. No word on minimum orbit distance. Fragmentation dangers? Ignored. This isn't blame, it's inherent to outreach science. Wonder draws crowds, hazard analysis doesn't. Then there's 3E Atlas, the star-hopping intruder, hogging spotlights despite its $1.8 Australian flyby, a comfortably remote mark. Outlets adore 3E Atlas for its enigma. Origin, outside our system. Hue, reddish or greenish, per varying data. It shifts tones, or appears to, which is odd. Typical rocks don't pull that. It has ignited debates on artificial speculations abound regarding its origins, from extraterrestrial scouts to signals hidden in its path. Such ideas may be improbable, yet they captivate. They draw clicks. They spark shares across platforms. In contrast, R2, the nearer intruder with its erratic path and episodes of flaring, receives subdued attention. It lacks that otherworldly allure. As a local from the solar system, likely originating in the Oort cloud, it carries no interstellar intrigue. Just your typical comet. Or so it seems. This one evaded detection until it loomed perilously close. It lurked amid the sun's brilliance, revealing itself only post-perihelion. It could break apart at any moment, and might yet do so. Its closest approach sits at a mere 7 million kilometers, worryingly tight. What captures the public's imagination hinges on the unfamiliar. 3i Atlas stands out as fresh. R2 does not. Thus, 3i Atlas dominates the news cycle, while R2 fades to a mere aside. Yet asides hold peril. They conceal the vital details. Caution is warranted in our outlook. Comets defy consistency. They surge in brightness without pattern. They dim erratically. They shatter abruptly. Forecasts draw from historical patterns, but each icy wanderer is unique. R2 could flare to magnitude 4, turning into a visible wonder for the unaided eye. Or it might drop to magnitude 8, vanishing from sight. Perhaps it splinters, scattering debris. Or it simply drifts onward, receding silently into the solar fringes, soon overlooked. Uncertainty reigns. One certainty, no collision threat exists. Projections place R2's Earth miss at 39 million kilometers. Far from impact range, yet near enough for complications. Near enough for potential fragment encounters. Near enough to boost meteor activity. Near enough that sudden breakup could send chunks veering toward our orbit. That's the essence of space hazards. Nuanced, not absolute. Not secure versus catastrophic. Rather, a web of probabilities riddled with unknowns. Our vigilance network, telescopes and monitoring arrays we rely on for alerts, falters against such variables. Built for steady, foreseeable bodies on fixed courses, it grapples when surprises arise. Objects lost in solar glare, sudden flares, or unexpected shedding. The system stumbles, and so do we. Now, let's delve further. We'll examine historical close calls, asteroids slipping by with scant notice, and the overlooked detections that occur far too routinely. Section 6. Real-world examples. Rocks spotted mere moments before or after their sweeps. Back in early 2025, the asteroid tagged 2025 TF zipped within roughly 400 kilometers of our planet's surface. 400 kilometers. That's tighter than the International Space Station's orbit, closer than countless satellites, encroaching on the realm of key orbital infrastructure, and it blindsided us right up to the brink. 2025 TF measures small, likely just meters wide. At that scale, atmospheric entry would yield a spectacular flare-up, but no surface harm. Recall the 2013 Chelyabinsk event, a 17 to 20-meter chunk that detonated overhead, equivalent to hundreds of kilotons of TNT. It wrecked windows, hurt over 1,000 folks, yet carved no pit. 2025 TF paled in comparison. It'd have been mere fireworks. But scale misses the crux. The issue lies in the delay of discovery. It snuck up undetected. It streaked above Antarctica, Earth's most isolated stretch, with minimal observers below. A slight shift in timing or path, and it could have overflown crowded zones. Zero heads up. This isn't a one-off. Lately, numerous diminutive asteroids pop up on radars mere days, hours, or minutes shy of perigee. Others get cataloged post-passage. They graze us unseen by scans, only betraying their presence as they depart. Such oversights stem from inherent constraints in our watch systems. Instruments demand a baseline luminosity. Tiny visitors glow dimly. Solar approaches render them undetectable. Swift transits outpace software tracking. Low reflectivity surfaces, dark, low albedo, camouflage against the void. This blind spot isn't abstract. It's a recurring, tangible flaw. We overlook objects frequently, and awareness dawns only when a vigilant eye scans the precise sky sector at the opportune instant, catching anomalous motion. The fallout runs deeper than assumed. Sure, most minor rocks disintegrate benignly on entry, but exceptions lurk. Even a modest fragment, striking precisely, can wreak havoc. A chunk mere meters across slamming into a satellite hitting something at orbital speed would obliterate it right away. Crashing into the International Space Station would prove deadly. Even a modest projectile slamming into an urban area might demolish structures and claim countless lives. Our atmosphere acts as a barrier, yet it's far from flawless. Items exceeding roughly 20 meters in size can make it all the way to the surface. Smaller ones still trigger destructive aerial explosions. Don't forget the problem of scattered remnants. As an asteroid disintegrates high up, it disperses chunks across a vast zone. Many bits are tiny, but others might pack enough punch to wreak havoc. Should the split happen above a crowded spot, those shards turn into deadly missiles. The Chelyabinsk incident flung meteorites across hundreds of square kilometers. Folks even picked them up as mementos. Yet had the body been bigger or the disruption lower down, the fallout could have turned lethal. Now amplify that scenario. Picture not just one minor asteroid, but a swarm of rubble from a crumbling comet. Swap a handful of rocky meters for multitudes, thousands perhaps, of particles from fine powder to massive stones, strewn along the path. Rather than one pinpoint strike, envision a scattered peril, a probabilistic risk where individual hits seem improbable. Still, the overall odds aren't trivial. That's the reality of comet breakups. They don't deliver a lone projectile. They unleash a barrage. Our two boasts an amoid of 7 million kilometers, the distance separating Earth's path from the comets. Should it shatter, with bits fanning out along the route, certain fragments could edge nearer. Not to collision course, not to direct contact, but nearer nonetheless. Near enough to bump the odds from insignificant to modest yet real. And modest yet real is plenty to unsettle those crunching the risk numbers. This draws from cases like 2025 TF and similar threats. Delays in spotting them are a genuine issue. We overlook plenty. We miss most if they're diminutive, swift, or approaching from odd angles. The space rocks we detect follow the script: foreseeable paths, expected origins, timely arrivals. The rule breakers? They're the terrors, precisely because they slip past our watch. Moving on, let's discuss why comets don't need a direct hit to pose threats. Leftover rubble and particle paths generate lingering dangers well beyond the main body's departure. Part 7. Comet breakup and particle trail risks. Plausible hypothetical cases. A comet might swing by without connecting, but its cast-offs can still sting. Here's the breakdown. Comets aren't sturdy boulders. They're flimsy clumps of frozen water, grit, stone, and carbon-based stuff, barely stuck by faint pull and sticky bonds. They're delicate by nature. Nearing the sun, heat strains fracture them. Gas release builds tension that rips them open. Gravitational tugs from nearby giants, if too near, yank them to pieces. At times, they crack subtly, dropping minor debris. Other times, they explode in a blaze, splintering into scores of parts. Take Comet Shoemaker-Levy 9 as the classic case. In 1992, it ventured too close to Jupiter, getting ripped by those gravitational stresses. Over 20 fragments emerged, elongating the orbital trail. 2 years on, they pounded into Jupiter sequentially, sparking colossal blasts seen from our planet. Every collision unleashed power rivaling millions of atom bombs. The marks on Jupiter's clouds lingered for months. It was awe-inspiring. It also highlighted comet vulnerability and the peril of their offspring. Consider another, Comet 73P/Vassman-Vakman. This one split repeatedly. Back in 1995, it divided into multiple segments. Then in 2006, it crumbled once more, yielding dozens of tinier bits. Skywatchers observed live as it fell apart, each piece sprouting its own fuzzy head and streamer. The shards kept diverging, tracing subtly varied routes. Gradually, they crafted a rubble flow, a stream of frost and powder tracing the prior path. Our planet has crossed sections of it. That sparked a short spike in shooting stars. Not world-ending, but evident. Now tailor this to R2. The comet's already flared out at least once, hinting at inner weakness. If it shatters, the sections will fan apart. The spread speed ties to their differing speeds, which hinge on the breakup's force. A mild division yields gradual drift. A fierce blast drives rapid scatter. Regardless, eventually, the pieces widen out, along with the grit they eject. That grit poses the true menace. Comets constantly flake off particles as ice turns to vapor. These specks are minuscule, microns to millimeters, but zip at dozens of km/s. At such velocities, a mere speck packs huge impact force. Striking a probe, it could bore through the shell. If it tags a sate, micrometeorites pose a serious threat in space, potentially harming solar arrays, instruments, or radio gear. Striking an astronaut during an extravehicular activity could prove deadly. Take the International Space Station, for instance. It's protected by defenses tailored to fend off these tiny intruders. These barriers consist of several layers meant to disintegrate approaching bits upon impact, stopping them from breaching the exterior. Yet, these protections aren't infallible. Bigger chunks, or those coming in at odd trajectories, can still break through. The ISS has endured numerous such collisions over the years. While most result in superficial harm, others have necessitated fixes. A thick trail of meteoroids, like those generated when a comet breaks apart, ramps up the danger considerably. Now, think about the orbital setup. The amoid of R2 stands at 7 million kilometers, marking the shortest separation between the comet's path and our planet's trajectory. Should the comet shatter and its pieces disperse along its route, a few could veer nearer to Earth's course. Not fully intersecting, not down to nothing, but nearer nonetheless. And if our world traverses that rubble trail at an inopportune moment, we could face an elevated barrage of debris that might translate to a more intense meteor display. It could spell trouble for orbiting satellites. It might lead to micrometeoroid strikes on missions in space. The odds of any single speck nailing a particular object remain slim. After all, the cosmos is vast and assets are tiny. Still, the overall likelihood that some impact occurs anywhere rises notably. Plus, we've got plenty up there these days, thousands of satellites, orbital outposts, even rudimentary probes. Each one serves as a possible victim. There's also the matter of how this interacts with our atmosphere. Should Earth plow through a heavy dust cloud, even with fine particles, the combined impact could show up visibly. Glow in the high layers might intensify. Bolide occurrences could surge, those dazzling fireballs that burst overhead. Hobbyists with telescopes would pick up on it. Networks of meteor cams would capture the oddity. It wouldn't spell doom, but it would stand out. And standout incidents often set off warnings. The true worry isn't the visible grit. It's the unseen boulders. A rock-sized fragment, say a meter or two wide, hurtling along at 30 kilometers per second, would stay hidden until the last second. Telescopes might spot it, but only by chance, if they're aimed at the precise sky sector right then. Coming from the sun's direction? Undetectable. With a low albedo, say, dark, non-reflective stuff, it'd be virtually impossible to detect. And landing over a crowded region? You'd get a Kelebinsk-level blast, or bigger. Gauging the odds here is tricky. We lack data on whether R2 has broken up. No clue if it will. Unknown how many shards it could yield or their spread. We don't grasp the sizes, speeds, or paths they'd take. All that's clear is the original comet's route, and that 7 million kilometers buffer to Earth's. Given those limits, we can deem the chance of a piece striking our planet as small. But small isn't non-existent. And when the stakes involve lives and key systems, small often feels insufficiently safe. Picturing it aids understanding. Envision the comet's path as a strand weaving through the void. Now picture that strand unraveling, branching into scores or hundreds of finer strands, each veering just a bit. Some cling to the main line. Others wander off. Over time, this swarm expands into a hazy band hugging the original track. Earth's loop is a separate strand, slicing across that band obliquely. Usually, we glide through clear voids, but at times we brush the band, and that's when the bits cascade earthward. This isn't mere theory without basis. Meteor showers embody this exact process. The Perseids, Leonids, Orionids, they're all remnants from comets. Annually, our planet cuts through these trails, yielding shooting stars. Typically benign, sometimes dazzling, seldom hazardous. Back in 1833, the Leonids unleashed a storm of tens of thousands of streaks hourly. Observers likened the heavens to a blaze. In our era, with all the orbital tech, such an event would wreak havoc. R2 isn't expected to spark a storm like that. Any ejecta it has is likely too thin, but certainty eludes us. It will until we observe it firsthand. And by then, options might boil down to mere spectatorship. Moving on, let's tackle a broader issue. Are we witnessing a wave of unexpected guests? Or is this simply skewed detection? Is the solar system hurling more arrivals our way? Or are we merely getting better at spotting them? Part 8. Spotting Trends. Are we in the midst of a rush of unforeseen callers? Allow me to enumerate them. Oumuamua showed up in October 2017. The inaugural verified interstellar wanderer spotted zipping by our system. It was peculiar, cigar-shaped, spinning erratically, speeding up in manners that defied standard comet venting explanations. It departed before we could fully probe it. Take a closer look at it. Next up was Borisov back in August 2019, marking the second visitor from beyond our solar system. Unlike the first, this was unmistakably a comet, complete with a fuzzy coma, a trailing tail, and a makeup that matched the kind of junk we'd anticipate from another star's leftovers. Fast forward to 2025, and we've got 3I/Atlas on the scene, the third such interloper. Experts debate whether it's more asteroid-like or a comet core, but either way, it's odd. It shifts hues dramatically. Truly bizarre. Meanwhile, as everyone fixates on 3I/Atlas, R2 slips through from right in our own cosmic neighborhood, staying hidden until well past its closest solar approach. That's 4 of these in just 8 years. Oumuamua, Borisov, 3I/Atlas, R2. They hail from varied sources, boast distinct makeups, turned up under different conditions, yet all caught us off guard. Each showed up with barely any warning, or none at all. Does this signal a trend? A spike in activity? Or simply the result of us at last tuning in properly? 3 main ideas explain it. Start with the first, detection skew. Our tools have leveled up big time. We've got superior scopes, broader sky coverage from surveys, and hobbyists diving into pro-level info. We're scanning more intently, so naturally, we're spotting more stuff. Setups like Pan-STARRS and the soon-to-launch Vera-C, Rubin Observatory are built for snagging fleeting phenomena, roaming bodies, shifting features, you name it. As these networks ramp up and sharpen, our hit rate climbs. This doesn't imply a flood of new arrivals. It just shows we're uncovering what was lurking all along. The second idea points to an actual uptick in orbital jostling. Perhaps the Oort cloud is getting a nudge from somewhere. A star that zipped by ages ago might have triggered a comet cascade heading our way, with the initial wave hitting now. Or our solar system could be cruising through a denser patch of interstellar clutter. galactic pulls from the Milky Way's framework might be herding extra comets sunward. It's plausible enough. The Oort cloud is vast, packing trillions of icy wanderers. Even a minor shakeup could dispatch thousands inward across millennia. To us, stuck in our brief lifespans, it'd seem like an abrupt rush. The third notion? Just random bunching in the stats. Sheer luck. Chance events create groupings. Toss a coin 100 times, and you'll get runs of heads or tails. No foul play, just how variability works. These 4 surprise guests over 8 years could be mere flukes, a blip without bigger implications. In the next 8, we might spot 0 or a dozen. Lacking extra info, it's tough to separate true patterns from the static. Supporting clues back each theory. The bias angle holds water. Known Earth-approaching asteroids have ballooned in the last 20 years, not from a sudden influx, but from targeted hunts. Comets likely follow suit. Swan has unearthed heaps of them, especially sundivers, thanks to its ability to glimpse what visual scopes miss. As our monitoring web grows, the inventory swells. Yet bias can't cover it all. Oumuamua was flat-out peculiar. Its cigar shape, odd non-grav push, no obvious coma. None of it added up neatly. Theories range from a planetary chunk ripped by alien tides to exotic ices like hydrogen or nitrogen bergs, or even frozen gas fragments. Ideas escalated wildly since the basics fell short. Then it zoomed off, robbing us of deeper probes. 3i/Atlas stands out too. Its tint flipped from reddish to greenish, or so some data suggests. Trust which readings? Rocks don't typically pull that trick. Hue ties to surface stuff. A shift hints at uneven layers, maybe from spinning to show varied sides or faint venting tweaking the light readout. Or who knows, something wilder. We're in the dark without a sharp close-up. R2 plays into this differently. It's no outsider, likely Oort-born and solar system local, but it lurked in solar glare, popping out only post-perihelion. It underscores how stuff evades us, even nearby. If R2 can vanish like that, imagine the rest. How many extended orbit comets zip inward yearly without a trace? No clue. We catch only the brighteners, the lingerers, the threshold crossers. Others? Invisible phantoms. A pattern? Possibly. The upbeat take. We're sharpening our view of a cosmos brimming with pop-ins, junk streams, and curveballs. The downer view. Influxes are ramping, and we're ill-equipped. Truth likely splits the difference. Where we're noticing more of these celestial visitors, not just because we're scrutinizing the skies more intently, but also because the underlying flow of cosmic wanderers turns out to be greater than previously estimated. Our solar system isn't some serene suburb. It's more like a bustling thoroughfare, and we're only recently setting up the surveillance gear to monitor it. Moving forward, let's examine the organizations handling this influx, the information channels, the delays, and the quiet periods that breed doubt. Section N. Organizations, quiet moments, and the journey of data to public view. Allow me to guide you through the path from initial detection to widespread awareness. Whether it's a seasoned expert or a dedicated hobbyist, someone detects an oddity, a drifting body, a suddenly glowing point, or a fleeting phenomenon. They log the coordinates, timestamp, and brightness. Next, they verify if it's already cataloged. If it's fresh, they submit the details. To whom? The Minor Planet Center, MPC, run by the International Astronomical Union. This hub processes reports on asteroids, comets, and similar minor objects from around the globe. It gathers inputs, cross-checks them, and releases notices once a discovery holds up. However, validation isn't instant. One sighting alone won't cut it. You require several to validate the object's existence, eliminate glitches from equipment, and compute an initial path. That involves pausing for additional sky watchers to aim their scopes at the identical sky region and back up the find. For dim targets, those teetering on the edge of visibility, or speedy ones, this could drag on for days or even weeks. Upon validation, the MPC grants a temporary label and distributes a digital bulletin. The info goes public, open to all, yet it's unprocessed. Orbital parameters, location data, brightness readings. This isn't crafted for the masses. It's specialist material, not a media blast or front-page story. Everyday folks skip MPC bulletins. They turn to journalistic pieces instead. And those pieces arrive down the line, assuming they do it all. In the interim, Other groups polish the trajectory details. NASA's Jet Propulsion Laboratory, JPL, operates Horizons, a tool for generating accurate paths of solar system entities. With incoming data piling up, the orbital model sharpens, error margins narrow, and forecasts gain solidity. Should the item seem risky, say, its path grazes Earth's vicinity, JPL marks it for attention. Then, the Center for Near-Earth Object Studies, CNEOS, assesses the danger level. If it's severe, NASA puts out an alert. If it's minor, silence might prevail. For R2, events unfolded in this manner. On September 11, 2025, amateur stargazer Vladimir Bezuki picked it up in swan imagery. He alerted authorities. Fellow spotters verified it through direct viewing. The MPC announced it as C/2025 R2 via a notice. JPL crunched the orbital numbers. CNEOS reviewed the threat. Verdict: harmless. Its nearest pass sat at 0.26 Australian dollars, safely distant. No media fanfare, no alerts to the public, merely a data entry tucked away in archives. That's the origin of the hush. Not from any cover-up or plot, but from a framework built for hazard control over crowd outreach. Non-threatening items stay off the radar, and without buzz, they fade from view for most. R2 popped up in select astroblogs and space sites, even snagging Astronomy Picture of the Day on September 18th. Yet it never went viral online or seized the headlines. Just one more comet amid the annual haul of scores. Compare that to 3I/Atlas, the interstellar oddity with its bizarre hue shifts and erratic speeding that screams for coverage. Such tales snag major outlets, ripple across social feeds, and spark endless debates. Doesn't matter that 3I/Atlas is benign, approaching no closer than 1.8 Australian dollars with zero peril. What counts is the intrigue, and intrigue drives clicks. This leaves voids when official bodies lag on clear, timely briefings. When the data flow crawls through jargon and the lag from spot to spotlight spans weeks or months, guesses rush in to fill it. Online crowds pick up on the lulls. They probe. Why the skimpy updates? What's with the radio silence? Are they concealing something? Without prompt rebuttals, wild ideas take root. Speculations, plots, whispers. Take Vladimir Bezuki's catch of R2 as a case study. He's no agency pro or full-time sky expert. He's a keen outsider skilled at parsing swan feeds. That he beat the pros to it doesn't indict the system. It highlights how the watch network has gaps, how offbeat routes count, and how key finds can hail from unlikely sources. Still, it prompts inquiries. If a hobbyist can unearth a comet, think about those gaps that professional skywatching efforts overlooked. What other things might be slipping past us? How many more items zip through the inner solar system without anyone noticing, simply because they're in the awkward spot at the awkward moment? Or because the telescopes are pointed in the opposite direction? Or the night sky's washed out by light pollution, the clouds are rolling in, or the gear's offline for repairs? We'll never be sure. It's impossible to pin down. That's the core issue here. The process for handling data is intentionally deliberate. Double-checking keeps out bogus detections. Prudence avoids needless alarm. Yet that same prudence opens up blind spots, and those blind spots breed uncertainty. When folks lose faith in official bodies to deliver straight facts, they turn to unofficial channels. And those channels aren't always trustworthy. Up next, we'll sift through the outlier notions, the conspiracy buzz, the offbeat hypotheses. We'll distinguish the ideas that merit a closer look from the ones that don't. Part 10. Outliers and Plots. To be upfront, expect folks to insist R2 isn't a natural formation. They'll call it a scout, a vessel, a manufactured gadget dispatched by some entity to keep tabs on humanity. They'll point out the path seems too neat, the schedule too spot on, the flares too deliberate. They'll accuse NASA of holding back details, burying photos, locking away the true findings. They'll declare it's a signal, an alert, an experiment, and they'll buy into it. So, let's sort through this step by step. We'll tackle each assertion individually and gauge if any warrant real scrutiny. First up, R2 is man-made. Could that happen in theory? Sure, a tech-savvy society might craft a probe disguised as a comet. They could sheath it in frost for a hazy envelope when it warms up. They could set it to flare predictably. They could tweak its course for a near-Earth flyby. It's doable, but far from straightforward, and it'd leave clues. If our two were engineered, we'd spot oddities. Spectral analysis would reveal weird mixes, rare elements, or compounds that clash with typical comet makeup. The core might display patterns, sharp angles, symmetries that raw space rocks don't have. The path would hint at precise nudges, subtle shifts unexplained by mere gas bursts. Plus, we'd pick up radio chatter, heat glows, or other signs of working tech. None of that's turned up. The light profile matches a standard comet. The haze aligns with vaporizing frost. The route obeys gravity's pull. No transmissions detected. Occam's razor favors the straightforward answer as the right one. R2 acts like a comet because that's what it is, suggesting artificial roots piles on extra premises, extra layers, extra players with hidden agendas and hidden tech. It's feasible, but not required. Science sticks to explanations that fit without extras. Second, the photos are being withheld. Do we get the full picture? Probably not entirely. Top-tier facilities don't release every shot they snap. They refine the info. They adjust for accuracy. They weed out glitches. They pick the sharpest shots. Certain datasets stay private for the scientists who requested the time. Others are too fuzzy to bother sharing. But suppression suggests a plot, a unified push to conceal stuff. That'd demand tight teamwork that's tough to pull off. Facilities are spread worldwide. They run on their own schedules. Hobbyists have their scopes too. If something striking showed up, it'd leak online fast. The absence of jaw-dropping visuals points to no such visuals existing, not a cover-up. Third, the path has been tampered with. Might some outside influence be guiding R2? If aliens are in play, it's back to the first point. If natural effects, absolutely. Gas releases cause extra pulls beyond gravity. Comets aren't straight shooters. They nudge their own paths with expelled vapors. R2's flares confirm it's doing just that, altering its direction. JPL's simulations factor in those non-gravity influences. They build in the venting. The path forecasts aren't flawless, but they're solid. Active steering would cause drifts the models couldn't blame on gas alone. Nothing like that. Fourth, it's benign yet loaded with symbolism. Certain voices say that regardless of R2's safety, regardless of no collision risk, its showing up carries weight. A symbol, a portent, a cosmic coincidence. That's not science talking. It's philosophy or faith at work. Science lays out the orbit, the makeup, the odds of a strike. It can't decode if the cosmos is whispering secrets. That's beyond testable ground. If a comet's timing speaks to you personally, fine. Just don't mix that inner insight with tangible threats. So, any ideas that call for deeper digging? Indeed. For starters, the risk of breaking apart and scattering fragments deserves its no conspiracy theory. It's basic physics. When a comet breaks into fragments that veer off from the main path, those bits can pose risks. Likely not from direct collisions, but rather as space junk, a stream of tiny meteoroids, or a danger to orbiting satellites, something we need to watch closely and plan against. Sure, it's hypothetical, yet it draws from solid knowledge of how comets act. The decision framework breaks down this way. Human-made causes seem impossible without proof. Hiding the images doesn't fit, considering how widespread the sightings were. Altering the path? Nothing points to that except normal gas releases. Symbolic interpretations aren't rooted in science. But debris from splitting? That's credible and merits follow-up. Wondering about possibilities is enjoyable. It's just how people work. We spot connections, assume intentions, and weave tales to plug the unknowns. Still, we must check those ideas rigorously with evidence. And if the facts don't back them up, we need the resolve to drop the notion and proceed. Now, let's change topics. We'll explore some fresh scientific news. We'll begin with brain science, since the mind functions as a sensing mechanism too, complete with its own oversights. Section 11. Brain Research. Scientists at UCSF uncover a protein that delays neural decline. Back in August 2025, experts from the University of California, San Francisco, released results about a protein that influences how brains age. Tests on older mice revealed this protein curbs the brain's ability to adapt. Once the team inhibited it, the elderly rodents displayed better recall and skill acquisition. Their nerve cells sparked more steadily. Connections between neurons grew firmer. In certain tests, their brain activity mirrored that of much younger animals. The setup was simple. Select mature mice, pinpoint the protein that builds up over time, suppress its function via medication or gene tweaks, and assess if actions enhance. The outcomes looked hopeful. Treated older mice excelled in recall exercises. They solved labyrinths more quickly. They identified items with greater accuracy. These changes were clear, consistent, and backed by strong stats. Yet this involves rodents, not people. Rodent brains are less intricate, tinier, and structured unlike ours. Successes in mice don't guarantee human results. Neuroscience's track record is full of fixes that healed animals but flopped in people. We've reversed Alzheimer's in mice countless times. Patients are still in limbo, so we must proceed carefully. These discoveries spark interest, though they're early stage. Should they apply to us, the consequences would be huge. Losing mental sharpness ranks among the top aging fears. Forgetting things, struggling to pick up new info, sluggish thinking. These erode freedom and selfhood. Halting even one such protein to ease or undo that slide could transform lives, not only personally, but for whole communities facing older demographics. Dementia costs the world trillions annually. Delaying its start by just years could free up immense funds and ease immense pain. Challenges exist, though. Proteins operate within webs, chains, and regulatory cycles. Targeting one could ripple outward, upsetting balances elsewhere. The study mice showed no clear downsides, but monitoring was brief. Extended impacts remain unclear, and people add layers of complexity. We endure longer. We gather more wear. We carry extra conditions. A neat fix in mice could clash oddly with our physiology. Consider this analogy. The brain serves as a scanner. It surveys surroundings, interprets inputs, stores experiences, forecasts outcomes. At its best, it seizes nuances. It adjusts. It absorbs. As it matures, acuity fades. Inputs dim. Interference builds. Recognizing shapes gets tougher. That UCSF-discovered protein plays a role in this wear down. Inhibiting it helped revive some of the brain's earlier sharpness. Reflect now on our cosmic observation tools. Observatories sweep the heavens, analyze data, list celestial bodies, forecast paths. Operating smoothly, they spot dim comets. They follow rocks. They alert to threats. However, these setups wear out too. Equipment ages. Detectors shift. Tuning slips, data flows fill with clutter, and gradually we overlook signals once detected easily. The comparison isn't exact, but it's revealing. Brains and scopes alike aim to discern order amid chaos. Both erode with time. Both might recover, somewhat, via fixes. For minds, perhaps a protein inhibitor. For scopes, maybe retuning, new detectors, better software. The core idea holds. Alertness demands upkeep. That UCSF research highlights how unseen processes shape our perceptions and our oversights. Occasionally, the underlying cause stems from biology, like a protein buildup linked to aging. At other times, it's rooted in technology, such as a sensor gradually falling out of calibration. Or it could be organizational, for instance, a polling routine that creates blind spots. Regardless, the fix remains consistent. Pinpoint the process, grasp its operations, and then step in to reinstate its effectiveness. Now, let's examine yet another key development in neuroscience. This one focuses on Alzheimer's, as the recurring cycle of bold assertions and tempered truths merits close attention. Section 12. The Alzheimer's Breakthrough Claim. In October 2025, a fresh surge of news stories emerged. Alzheimer's cured in mice, they proclaimed. The coverage buzzed with excitement, while online shares brimmed with optimism. Yet the truth proved far more intricate. Scientists had experimented with an innovative approach, perhaps aimed at repairing blood vessels, or eliminating amyloid buildup, or modulating protein levels. The specifics shifted across reports, but the core idea held steady. Older mice exhibiting memory issues displayed gains following the therapy. Plaques in their brains diminished. Recall abilities enhanced. Certain indicators even showed disease markers receding. This isn't a novel occurrence. Over the last 20 years, Alzheimer's investigations have yielded numerous encouraging results in rodent experiments. Immunizations targeting amyloid, medications tackling tau tangles, genetic treatments boosting neural connections. Such methods succeed in mice. But in people, the majority falls short. The leap from lab animals to humans is vast. Rodent simulations of Alzheimer's fail to mirror the complete human condition. Rodents' lifespans are too brief to manifest the entire range of damage. Their neural structures are less complex. Immunity operates differently. Metabolic rates accelerate. What thrives in a brief 6-month rodent trial could crumble in a decade-long human evaluation. Participant numbers count heavily. Rodent experiments typically involve mere dozens. Human studies demand thousands. Time frames are crucial. Animal tests span months. Clinical ones stretch over years. Adverse reactions play a role. Something harmless in mice could prove harmful to us. Effectiveness is key. A therapy boosting memory 20% in rodents might yield just 5% in humans, and that slim margin may lack real-world impact. Summaries in outlets like Newsweek, much like other mainstream science pieces, spotlight the upbeat angles, reversals, advances, prospects, phrases that drive engagement. In contrast, the original studies, the peer-reviewed publications, adopt a more reserved stance. Terms like initial, constrained, and demands additional investigation appear frequently. They highlight the hurdles in applying findings to humans. Victory isn't declared, incremental steps are noted. The core issue here is straightforward. Intricate discoveries morph into flashy titles. Subtleties vanish. Ambiguities disappear. The divide between genuine discoveries and widespread misconceptions widens. Then, when therapies flop in human testing, when trials report null results, audiences sense deception. A remedy was dangled. Instead, letdown followed. Confidence wanes. This cycle extends beyond Alzheimer's. It surfaces wherever risks loom large and knowledge grows tangled. Oncology, environmental modeling, epidemiology, and indeed, celestial studies. Spot a fresh comet, and reports hype dazzling shows, rare spectacles, easy viewing without aids. Truth often dims, fainter glows, shakier outcomes, reliant on unpredictable factors. Comets dim out. They break apart. They underwhelm. Crowds anticipating wonders end up deflated. The takeaway? Cultivate doubt, not dismissal. Doubt wisely. Encounter a story touting a major leap. Dive into the source material. Scrutinize group sizes. Seek out qualifiers. Probe what data was collected versus what conclusions were drawn. Inquire about constraints. Consider future steps. Usually, the response boils down to further work required. And that's acceptable. It's science's rhythm. Headlines, though, crave absolutes. Research navigates odds. The connection to R2 runs deep. The comet exists. Data points hold true. Trajectory math checks out. Yet forecasts on luminosity, breakup risks, they're all estimates of chance. Outcomes remain unknown. Possibilities, weighted by confidence levels, are what we have. The ethical path forward? Convey those odds transparently, neither exaggerating nor minimizing, steering clear of sensational lures. Moving on to artificial intelligence next. A realm where buzz often outpaces fact, yet one where genuine advances are reshaping our vigilance against space hazards. Section 13. AI Advancements, Tool Launches, and Moral Debates in October 2025. That month featured multiple reveals in AI. Fresh architectures, innovative applications, expanded functions, and freely available code that stretches machine intelligence's boundaries. Core systems boasting sharper logic, superior grasp of context, quicker processing speeds. Firms and academic teams rolled out platforms capable of handling extended in various fields. AI helps sustain logical consistency through intricate thought processes, produces programming code with greater dependability, and interacts seamlessly with diverse input types at once. The rate of advancement remains unyielding. Tasks that felt out of reach just 2 years back are now standard operations. Today's everyday methods will likely fade into irrelevance within another 2 years. This speed-up is genuine, quantifiable, and displays no hint of easing up. Running parallel to the technological strides and moral efforts are efforts to synchronize AI evolution with core human principles, introduced at international gatherings and supported by experts and officials. Specifics differ across cases, yet the central message endures. AI holds immense power. It's gaining speed rapidly, so we must ensure it matches our genuine aspirations, not merely surface-level desires. but profound priorities that hold up under actual outcomes. The core issue isn't solely AI's capabilities, but its proper applications. And who holds the authority to determine that? These aren't vague theoretical debates. They're pressing, actionable issues. With AI growing ever more proficient, self-reliant, and woven into vital systems, the risks escalate. An error in health assessments could prove fatal. A flaw in transportation management might spark crashes. A slip in space monitoring could blind us to approaching dangers. Within astrophysics, AI already forms a key part of data processing workflows. This isn't conjecture, it's established routine. Computer-driven anomaly spotting reviews telescope photos to spot fleeting phenomena. Learning-based models sort celestial bodies, separating rocky bodies from fixed lights, icy wanderers from vast clusters, exploding stars from flickering ones. These sorts occur in a blink, mere fractions of a second. A person might need minutes or even hours for identical analysis. Programs hone path predictions, using batches of location data to compute paths. They forecast upcoming spots, gauge margin for error, highlight items whose paths near our planet. They mark possible dangers, bodies that could lead to impacts, prompting extra scrutiny or inclusion on alert rosters. The sheer data load exceeds what people can handle by hand. Contemporary broad coverage scans produce terabytes of info each evening. Every photo holds millions of potential targets. Each requires sizing, logging, and matching against prior records. Short-lived changes, items that emerge, vanish, or shift in glow, demand detection and noting. Once the Vera Rubin Observatory reaches full capacity, it will capture the whole observable universe every several nights. It will spot billions of entities. Among them, tens of thousands will shift position, alter form, or flicker briefly. No group of experts could tackle that influx alone. AI is essential to comb through it all, unearthing key insights amid the clutter. Absent such tools, current stargazing would falter under its triumphs, swamped by the endless stream of details from scopes nightly. Yet AI isn't flawless. It errs. It highlights bogus threats, items resembling risks but proving harmless. A high-energy particle strikes the sensor, creating a vivid line. The system interprets it as a swift traveler. It tags it as a possible near-Earth rock. Subsequent checks reveal emptiness. The supposed item was illusory, a defect, a mirage, or simply a wrong sort by the machine. A far-off stellar blast intensifies slowly. Its brightness pattern mimics a pulsing light. The AI slots it incorrectly. Days elapse until someone spots the mistake and corrects it. At that point, the prime viewing slot has passed. Vital observations are gone. It overlooks true alerts too, particularly odd ones that stray from learned patterns. AI models draw from samples. Feed it countless rocky examples, and it grasps their traits. Provide myriad icy ones, and it masters those appearances. But what if a newcomer defies the samples? What if its features lie beyond the range the system studied? It could dismiss it as clutter, a flaw, or something dismissible, or slot it wrongly, routing it to the improper track. In any case, the important cue vanishes, and it can heighten prejudices. If the learning data skews toward specific object kinds, the AI inherits that slant. Imagine most examples come from visual scans in select sky regions, during particular seasons and weather. The system absorbs those habits. It expects certain luminosity levels, hues, and speeds for such bodies. Then comes a deviant, perhaps unusually dim, with low reflectivity bouncing back scant light, or traveling at unexpected velocity, or emerging from an odd angle. The AI, shaped by the uneven data, fails to identify it. It discards it. It snags only what's familiar from training and overlooks the rest. There's also the deluge of interference issue arises as AI improves its anomaly detection, producing a flood of notifications. At first glance, this seems beneficial. Greater detection rates imply broader surveillance and fewer overlooked items. Yet, the influx of alerts demands extensive verification. Each verification requires additional telescope access, personnel involvement, and overall expenditure. Major observatories charge thousands of dollars hourly, making unrestricted pursuits unaffordable. Prioritization becomes essential, discerning which targets merit the allocation and which do not. An elevated false positive rate can saturate the process. Researchers end up pursuing illusions, neglecting genuine dangers in the process. Striking a balance between sensitivity and specificity proves challenging. Sensitivity measures the system's prowess in identifying true signals, while specificity gauges its skill in dismissing spurious ones. Ideally, both metrics peak, but reality imposes compromises. Boosting sensitivity uncovers more authentic finds alongside increased false alarms. Heightening specificity filters out more falsehoods, yet risks bypassing legitimate detections. The optimal equilibrium, snaring most valid hazards without excessive false triggers, remains elusive and fluctuates. Factors like data integrity, environmental viewing parameters, and target traits influence it. Ongoing adjustments, iterative responses, and human supervision are indispensable. Consider this imagined case. An AI scrutinizing comet luminosity records spots an irregular surge in R2's luminosity profile. The comet had been intensifying progressively post-discovery, aligning with escalating solar exposure during its inbound path. Abruptly, on October 15th, the luminosity surges sharply, not dramatically, perhaps just half a magnitude, but the rise is steep and unforeseen, deviating from anticipated gradual shifts. It resembles an outburst, though the schedule feels off-kilter. The sequence diverges from prior events. Earlier outbursts occurred near perihelion under peak solar influence. This occurrence unfolds weeks afterward, as the comet recedes from the sun. Such timing is atypical. Could it be authentic? Or merely a device malfunction? Perhaps a misalignment in telescope tracking. Atmospheric variations might interfere, or calibration could falter. Alternatively, might it signal an unforeseen development, a physical alteration in the comet, like debris expulsion, meteoroid impact, or a volatile reservoir erupting violently? The AI lacks physical insight. It doesn't grasp comet dynamics or possess behavioral simulations. It merely cross-references against familiar patterns. This outlier prompts it to highlight the irregularity and escalate to a specialist. The astronomer gets the notification amid a barrage of others. That day, she reviews the records, notes the peak, and cross-checks auxiliary sources. Has R2 been monitored lately by peers? Do separate readings validate the luminosity shift? Database queries yield no matches. The anomaly surfaces solely in this one collection, raising doubts. Instrumental glitches often confine to isolated records. Authentic phenomena typically register across various logs, barring fortuitous timing where just one scope captured the moment. She inspects the session records. Any glitches that evening? Telescope malfunctions, sensor troubles, meteorological disruptions? Entries note patchy clouds and fluctuating clarity, but nothing out of the ordinary. Pre- and post-peak imagery reveals a standard comet. No evident morphology shifts, fresh debris, or sustained glow afterward. The peak appears fleeting, assuming its legitimacy, possibly mere fluctuation or a transient event too short for corroboration. She weighs the options. The data remains inconclusive. Though the surge might hold truth, it's likely spurious. Lacking backups or extras, broadcasting a warning feels hasty. It would drain funds, spur extra scans, rally colleagues, and, should it prove baseless, squander collective effort. Opting against escalation, she archives the irregularity as unverified and shelves it. Onward to the subsequent notice. Operations persist, but suppose it signified something substantial? Imagine the peak heralded disintegration, with shards now veering from the core path. The specialist's choice, amid ambiguity and partial info, could overlook a key detail. Debris needs duration to detach noticeably. Initially, in mere hours or days, it's proximate to the nucleus, hard to distinguish even under superior optics. Once spaced sufficiently for individual identification, deviations might render them independent risks. The AI that detected it gets sidelined, not through oversight. The expert adhered to guidelines, assessed the proofs, and rendered a sound judgment. Yet judgments amid doubt occasionally err. Gradually, operators grow wary of AI notifications due to frequent most alerts turn out to be false positives. This phenomenon, known as alert fatigue, has been extensively documented in areas like medical diagnostics, aviation security, nuclear facility management, and increasingly in astronomical observations. When warnings blare frequently without leading to real issues, individuals begin to respond less urgently. They start ignoring them. They create mental shortcuts to sift through the clutter. Perhaps they'll only act on notifications with confidence levels exceeding 90%. Or they might pursue leads only when several devices highlight the identical anomaly. Or they could downplay signals from outdated observatories plagued by calibration problems. Such shortcuts make sense. They conserve effort. They direct efforts toward the most viable prospects. Yet occasionally, these shortcuts block out the true indicators as well. The authentic danger, the one that truly counts, could register just 85% confidence. It might be detected by a single device simply because that was the only one pointed in the right direction at the moment. It could originate from an aging telescope that, for all its flaws, still captured something genuine. And when such a notification appears, it's brushed off as irrelevant clutter. The very pattern spotting skills that enable people to manage data overload can also obscure real outliers. This underscores the hurdles in blending human and AI efforts. Neither side is flawless. AI excels in speed but lacks depth. It sifts through enormous datasets in mere moments. It uncovers patterns that would consume humans hours to discern. It never wearies. It maintains unwavering attention. However, it fails to grasp nuances. It lacks gut instincts. It can't assess if an irregularity aligns with physical principles. Humans, by contrast, operate more deliberately but with greater insight. They comprehend the laws of physics. They possess intuition. They evaluate cause and effect and feasibility. Yet they are constrained by focus limits, exhaustion, and mental prejudices. They can only scrutinize a fraction of the information. They overlook events beyond their current scope. The optimal setup leverages their strengths together. With AI tackling the sheer volume and humans providing discernment, AI combs through all inputs, highlights deviations, and hands them off for human review. Experts then scrutinize the candidates, incorporating background knowledge and instincts to separate valid signals from junk. Success depends on mutual reliance, fine-tuning, and iterative improvements. People need confidence that AI isn't overlooking vital cues. The AI requires adjustment to deliver useful alerts without flooding the system. Feedback mechanisms are essential, allowing humans to inform the AI of accurate or erroneous outputs, enabling ongoing refinement. Moreover, humans must stay alert, avoiding overconfidence and the belief that AI covers every base. The instant people view AI as error-free, a flawless sentinel that detects all threats, the setup turns risky. After all, AI isn't infallible. It's a potent yet bounded instrument that demands human supervision to operate effectively. The real peril isn't AI's shortcomings. It's excessive faith in AI leading to diminished vigilance. Once attention wanes, oversights proliferate. Detection now extends beyond mere equipment. It's no longer solely about constructing larger scopes with superior optics and heightened sensors. It involves code. It encompasses routines. It includes branching logic, deep learning models, and probabilistic cutoffs. It's the guidelines we devise to differentiate meaningful data from interference. The simulations we develop to forecast paths. The workflows we design for handling inputs. All this stems from human ingenuity, shaped by human-curated datasets and applied in human-defined scenarios. The prejudices, omissions, and oversights, those are human imprints, deliberate or inadvertent. They permeate the architectures we create. AI extends our gaze, but it can't resolve the core dilemma. We're seeking structures in a cosmos indifferent to our success. The universe doesn't tailor itself for easy spotting. It doesn't simplify matters. Bodies approach from awkward directions at untimely moments, bearing traits that deviate from our prepared examples. They lurk amid solar interference. They show up amid adverse conditions. They break apart erratically. Our spotting frameworks, whether human-driven or machine-based, must evolve to confront this unpredictability or perish. The task isn't merely crafting superior instruments. It's fostering superior synergy between instruments and their operators. Moving forward, we'll draw on another brain science investigation. This one explores spatial recall and its waning with age, serving as an analogy for the gradual erosion of spotting mechanisms. Part 14. Metaphor of instrument and sensor wear. Stanford's work on spatial memory and aging. On October 3, 2025, Stanford scientists released results detailing the drop in spatial memory within maturing brains. They examined cells in the hippocampus, the cerebral area tasked with constructing mental layouts of surroundings. These aren't vague diagrams. They represent neural encodings of tangible locales, forged through encounters and honed via steady practice. In juvenile creatures, these nerve cells activate dependably whenever the organism reaches a particular spot. The activation sequence is exact, steady, and repeatable. For instance, neuron A activates upon entering corner 1. Neuron B triggers in corner 2. This sequence forms a cognitive blueprint, a brain-based grid that enables the creature to recognize its position and plot a route to its desired destination. However, in older specimens, these cells respond with diminished dependability. Neuron A could activate in corner 1, or perhaps in corner 2, or fail to activate entirely. The blueprint turns hazy. Spots merge indistinctly. The creature remains aware of being in a general area, yet that area lacks sharpness. Orientation grows more challenging. The creature pauses uncertainly. It retraces steps. It veers off course. Ultimately, it arrives at the objective, though the journey proves roundabout, erratic, and riddled with blunders that a youthful counterpart would avoid. Researchers pinpointed the process driving this deterioration. Specific proteins build up over time, attaching to synapse receptors and curtailing adaptability. Synaptic plasticity refers to the capacity of neural links to intensify or diminish according to experiences. It underpins the mechanisms of learning and recollection. As adaptability wanes, these cells forfeit their knack for refining the blueprint, fixing inaccuracies, or integrating fresh data. Consequently, spatial encoding deteriorates. The blueprint persists, yet it grows obsolete, vague, and undependable. The creature persists in orienting itself, albeit with reduced precision. It errs more frequently. It requires extra time to locate targets. The downturn unfolds slowly, initially understated yet quantifiable. Gradually, it intensifies. Mistakes pile up. The blueprint erodes. This discovery extends beyond mere brain science. It serves as an analogy for any sensing apparatus humans have constructed. Observatory optics age in a strikingly similar fashion. Devices begin with keen acuity, finely tuned to capture the weakest emissions, but gradually they falter. Alignment in the optics shifts subtly. The reflective surfaces channeling stellar light rest on frameworks that swell and shrink amid thermal fluctuations. Across months and years, minute displacements build. Sharpness dulls. The image diffuses. Rays meant to concentrate on one sensor element disperse over multiple. The point spread function, the formula outlining how an observatory depicts a pinpoint emitter, widens. Clarity diminishes. Surfaces gather particles. Even in top-tier facilities, even under controlled conditions, fine debris alights on the lenses. Debris diffuses illumination, cutting the flux arriving at the sensor. More severely, certain observatories face open exposure. Breezes haul abrasive particles. Thermal swings provoke moisture buildup. Eventually, the surface tarnishes through oxidation. The metallic layers, designed for high reflection, wear down. Efficiency falls from 98% to 95% to 90%. Each drop in percentage translates to fewer particles detected. Dimmer entities evade notice. In the end, the surface demands removal and recoding, an undertaking spanning weeks and costing hundreds of thousands of dollars. Detectors accrue flaws. Charge-coupled devices. The semiconductor arrays transforming light particles into electrical charges, sustain harm from cosmic radiation. Energetic particles collide with the crystal structure, dislodging atoms and generating flawed spots that yield spurious outputs. Inactive spots emerge. Regions where light hits yet yields no output. Interference motifs arise. Recurring distortions that require correction and data handling. The sensor continues operating, but its response spectrum narrows. Its responsiveness fades. Targets at the detection edge, yielding just a few particles per scan, sink beneath the interference level. They disappear. Tuning grows coarser. All observatories demand periodic tuning to translate sensor readings into valid data. You aim at reference stars of established luminosity, gauge the output, and construct a response graph. Yet tuning wanders. Sensor behavior alters, light passage varies, atmospheric conditions shift. Without frequent retuning, data loses reliability. A source deemed magnitude 6 could truly be 5, 8, or 6.2. Such variability cascades. Luminosity assessments turn suspect. Trajectory forecasts reliant on luminosity stray further. Uncertainty margins expand. Images blur. Detection limits climb. Entities once clearly spotted, once yielding firm signals, now teeter on the brink of mere probability. Is it a comet or an artifact? A transient body or a radiation strike? Doubt mounts. Analysts grow wary. Verification scans prove necessary, yet access to instruments remains limited. When each borderline signal demands validation, operations stall. Backlogs lengthen. Targets slip away unverified. They escape us. Upkeep mitigates issues, though only so far. Surfaces can undergo polishing. Particles yield to gentle abrasion or blasts of purified gas. But polishing brings there's a hazard involved. A mere nick, a streak, or some lingering buildup. These issues can exacerbate problems. Restoring the mirror's shine through recoating revives its reflective properties, yet it demands extracting the mirror, transporting it to a specialized facility, enduring weeks of processing, followed by reinstallation and realignment. In the interim, the observatory lies dormant. Data collection halts. The ongoing survey grinds to a stop. Celestial bodies that could have been spotted during that period slip through the cracks entirely. Detectors can be swapped out. Upgraded CCDs offer improved quantum efficiency, reduced interference, and broader dynamic range. Such options exist on the market, but swapping them comes at a steep price. One unit alone might run into millions of dollars. Fitting it in involves meticulous care. The device needs chilling to near absolute zero to minimize heat-induced noise. The cooling setup requires ongoing upkeep. Seals can break, compressors break down, subsystems falter, and even with a fresh detector, the broader optical pathway continues to wear down. An observatory's effectiveness hinges on its most vulnerable part. Recalibration is possible in theory. Ideally, you'd adjust it nightly via reference stars, verifying the baseline brightness and gauging atmospheric absorption. Reality throws curveballs, though. Weather patterns disrupt plans. Timelines shift. Computerized workflows rely on outdated adjustment data. The gradual shift escapes notice until an inspection reveals skewed readings. At that point, potentially weeks or months of observations could be tainted. Trajectory computations based on those figures propagate the inaccuracies. Targets end up misplaced. Forecasts fall short. Yet upkeep demands substantial effort, scheduling, funding, and specialized knowledge. Resources are limited. Granting bodies favor launching fresh initiatives rather than sustaining established ones. After a telescope launches and starts delivering, the initial buzz dissipates. Media coverage shifts elsewhere. The creators who conceived it step away into retirement. The technicians who assembled it shift to novel endeavors. The hosting organization inherits a deteriorating apparatus amid dwindling allocations. Routine servicing gets pushed back. Enhancements are delayed indefinitely. Where outpaces fixes, inevitability prevails. Research from Stanford illustrates that even self-sustaining organic structures, which renew themselves non-stop, succumb to deterioration over time. Brain cells falter in performance. Even as the organ forges fresh links, trims redundant pathways, and restructures its wiring. The hippocampus stands out as one of the rare zones in the brain generating new cells lifelong. Neuron formation persists well into seniority. Still, despite this renewal potential, navigational recall fades. Fresh cells fail to offset the buildup of harm entirely. Connections erode, proteins build up, cognitive charts turn faulty. The breakdown proceeds more gradually than absent such renewal. But it's unavoidable nonetheless. Our stargazing tools lack this advantage. They aren't self-maintaining. They don't renew on their own. Harm, once inflicted, lingers until deliberate action corrects it. Such action tends to be sluggish, costly, and partial at best. A polished reflector today picks up grime by tomorrow. A swapped sensor today develops faulty spots by next year. An adjustment performed today veers off course next month. The erosion presses on without mercy. It accelerates beyond what's seen in living systems, lacking any inherent mending process. And as these tools falter, opportunities vanish. R2 exemplifies how oversights and spotting arise. The comet surfaced belatedly, concealed in a positional shadow amid solar brightness. But shadows aren't solely spatial. They can stem from equipment limitations. A dim comet teetering on the edge of visibility might register clearly on a modern scope with a newly resurfaced mirror and flawless sensor. The identical comet, viewed months afterward through the same setup, now marred by settled particles and dead pixels, could vanish from view entirely. The target remains unaltered. The instrument has shifted. Due to this decline, the observation misses the mark. Identical targets examined via the same method yield varying outcomes based on the tool's condition. This isn't mere speculation. It occurs routinely. Wide-area observatories identify diminishing numbers of entities in their mature phases compared to initial ones. Despite the unchanged cosmos, the drop-off traces to matured components, compromised lenses, and detector breakdowns. Failing to address this, skipping routine evaluations and adjustments, neglecting to monitor tool efficacy longitudinally, leads to overlooking items once routinely captured. We remain oblivious to these omissions since they never register in records. They haunt as unseen phantoms, untraced, undiscovered. Another factor is data overload, a distinct form of wear. Observatories churn out massive data troves. Contemporary broad-sky programs yield petabytes annually. Each frame packs millions of data points. Each point holds a reading. Handling this influx calls for automated chains, software suites that spot features, determine coordinates, gauge brightnesses, match against databases, compile lists, and highlight oddities. These chains operate non-stop, absorbing fresh inputs and generating outputs. Yet as the flood intensifies, the chains buckle. Computation durations data piles up. Indicators emerge. Information cues. A photo captured this evening could linger unanalyzed until the following day or even the week after. Once an irregularity is spotted, once a person reviews it and determines it warrants further action, the item has already shifted position. The monitoring period ends. We forfeit the opportunity to verify, to fine-tune the path, to evaluate the threat. Storage capacity poses yet another hurdle. It demands setup, storage devices, computing units, climate control, duplicates, safeguards. Everything involved incurs expense. As funding shrinks, capacity gets trimmed. Archived records shift to sluggish formats. Real systems that require hours to retrieve. Should you require re-examination of past visuals, should you hunt for a dim entity overlooked initially, you endure delays. You file a petition. You await the real mounting, the info migration, the computation wrap-up. Time drags on, and the target vanishes. Alertness demands upkeep, not merely of equipment, but of code, protocols, and collective expertise. Code harbors flaws. Workflows embed presumptions. A cutoff established half a decade back may no longer suit. The heavens evolve. Urban glow intensifies. Orbital networks proliferate. Streaks and bursts in each frame surge dramatically. The workflow marks them as outliers. The lineup swells with misleading alerts. Genuine outliers sink beneath. Tuning the cutoff proves tricky. Alter it excessively, and genuine items slip away. Alter it insufficiently, and the misleading alerts persist. An individual must oversee the workflow, adjust the settings, validate the outcomes. That individual requires skill, background, shared insights. Skywatchers step aside. Tech specialists advance elsewhere. Those who crafted the setup, grasp its oddities, pinpoint the gaps, recall the rationale behind choices, they depart. Records aid, yet remain incomplete. Nuances fade. Fresh arrivals join. They grasp the setup, yet lack deep familiarity. They miss the gut feel honed over years. Errors occur. A setting shifts sans grasp of ripple effects. A tuning document updates erroneously. A supposition arises that once got debated and dismissed. The incoming group ignores the backstory. They recycle past blunders. The setup veers from peak efficiency. Spotting efficiency drops. Awareness dawns only when a review uncovers overlooked targets the scope ought to snag. The likeness to maturing minds rings true. Each begins keen, erodes slowly, dulls perception, overlooks cues. Each calls for deliberate care to curb the slide. Each ultimately falters despite top efforts. The fix mirrors that. Revamp, retune, modernize, swap worn parts for fresh. Mentor successors. Log all details. Foster enduring wisdom. Combat disorder across tiers. Aware victory stays fleeting, yet aiming to postpone the endgame just long enough to count. The Stanford team demonstrated that halting age-linked proteins in rodents revived certain navigation recall. The fix didn't revert elderly rodents to youth. It eased their age. It tempered the slide. It extended the clock. That's upkeep's role for scopes. It skips peak new revival. It tempers the wear. It stretches the timeline. Timeline to spot the next R2, the next surprise guest, the next form lurking in brightness or detection's fringe. Timeline counts as the prime asset. As setups crumble, as spotting falters, as where prevails, we squander timeline. And timeline loss equals foregoing the view of incoming threats pre-arrival. Now, to conclude, we'll cover upcoming steps, key watches, advocacy points, and ties to Apophis, the asteroid slated for 2029. Section 15, Worldwide Summary, Future Watches, and Project Outline. If R2 signals alarm, here's our path ahead. The comet nears peak proximity on October 20th, 2025 at 0.26 Australian dollars. That's 8 days out. In the interim, these actions must unfold. Initially, position forecasts. Monitor the course. Polish the path. Scan for deviations. Gas release generates extra pulls. Should the comet surge once more, eject unevenly, the course adjusts. Not drastically, but potentially decisively. Sustain observations. Sustain refinements. Shun the notion that today's model locks in. Next, spectral analysis and radio imaging. We must discern R2's makeup. Spectral scans reveal the hazes blend, venting vapors, existing compounds. Radio imaging, should the comet near sufficiently, and we aim suitable arrays, might outline the core, gauge dimensions, spot spins, perhaps glimpse features. This transcends mere intrigue. Makeup shapes comet action. High volatile cores surge fiercer. Form influences. This raises concerns about potential breakup risks. Should the core consist of a loosely aggregated pile of rubble pieces barely held by faint gravitational forces, it could disintegrate easily. Conversely, if it's a sturdy, unified body, it would remain whole. Determining its nature is essential. Next, pursue detailed imaging efforts. Attempt to discern the core structure. Seek out any separated parts. In case R2 is fractured, with segments beginning to separate, we must spot them immediately to plot their paths. Initially, such pieces drift apart gradually. Detecting them sooner allows for more accurate forecasts of their destinations. Additionally, track dust and particulate matter. Scan for comet tails. Monitor expulsion incidents. Watch for meteor activity. Ground-based cameras can pick up incoming particles as they pierce the atmosphere. Orbital detectors can gauge the influx of tiny meteoroids. Should R2 be releasing material, or if our planet nears a flow of such ejecta, early alerts are vital. Just a handful of hours' notice suffices to safeguard satellites, shifting them to safe postures, angling solar arrays sideways, minimizing their exposed profiles. Moreover, simulate threats to space assets. The International Space Station circles at roughly 400 kilometers altitude. Other satellites span heights from low Earth orbits to geostationary ones at 36,000 kilometers. Each represents a possible victim. A concentrated stream of meteoroids heightens impact probabilities. Though the overall danger stays minimal, minimal is contextual. If the normal rate is 1 particle per million cubic km per hour, and a debris flow boosts it to 10 particles per million cubic km per hour, that's a tenfold surge. Even modest counts escalate when scaled across vast spaces and extended durations. Simulate the particle density, assess the dangers, and devise backup plans. Turning to governance and infrastructure, what must we require from the organizations tasked with our safeguarding? Primarily, fund vigilant monitoring toward the sun. The majority of our observatories face outward, away from solar glare. a logical choice since the sun overwhelms detectors. Yet, threats emerging from that solar sector remain hidden until they clear the brightness. We require orbital scopes strategically placed to peer sunward. Specialized gear capable of spotting comets and asteroids amid the dazzle. Missions like SOHO and SWAN have demonstrated feasibility. We need expanded arrays like them, focused on comet spotting across broader wavelengths. Secondly, establish instant sharing data channels for the public. Openness fills the void left by secrecy theories. With prompt release of sightings, live updates to path calculations, and straightforward explanations of margins of error, confidence grows. Speculation fades when information flows freely. The Minor Planet Center and JPL offer some of this already, though their tools suit experts. We demand user-friendly portals, graphical displays, and simple breakdowns. Render the info approachable and comprehensible. Thirdly, foster global teamwork. Observatories of the world, spanning zones, skies, and technologies. A synchronized network enables non-stop surveillance. As one site drops the target beyond its view, another assumes coverage. Warning systems require uniform standards. If a facility identifies a threat, how fast does that intel spread to peers? To leaders? Seconds count, as do minutes, hours, and days. Consider Apophis for comparison. Asteroid 99942 Apophis, about 340 meters across, will zip past nearer than geostationary satellites on April 13, 2029, under 4 years from now. We've tracked Apophis since 2004, over 2 decades of data yielding a razor-sharp orbital model. We pinpoint its position on that date to within kilometers. Impact is off the table. It'll skim by at around 31,000 kilometers, tighter than certain satellites, yet secure. Ample lead time lets us ready gear, scrutinize it during the encounter. Apophis exemplifies the foreseeable threat, anticipated, observable, drawn out. R2 embodies the contrary, erratic, freshly spotted, orbit hazy, makeup mysterious, breakup possible. R2 unnerves experts not for direct strikes, but for its near-miss detection. Similar lurkers exist unseen. More await discovery too late. The gap between Apophis and R2 boils down to preparation window. Apophis afforded decades. R2 offered mere weeks. In planetary protection, time is paramount. For scrutiny, path refinement, strategy assessment, decisive steps. Exhaust that, and choices vanish. You're stuck observing, wishing, beseeching that the figures align. Errors don't tip adversely, splinters don't veer into collision paths. Foreseeable big bodies draw focus. Apophis will face intense probing. Telescopes will train on it universally. Radars will probe relentlessly. One close shave will yield asteroid insights surpassing years of remote gazes. That's progress. Yet peril stems from the stealthy arrivals. Diminutive, swift, unforeseen, the wild cards lurking in solar blindness, emerging from blind spots. Unexpected threats, the kind that flare up just when we've glanced elsewhere. That's what sneaks up on us. The cosmos isn't out to destroy humanity, nor is it rooting for our survival. It's neutral. Debris hurtles across the void, guided by gravitational pull and inertial force. Occasionally, it intersects our trajectory. Many veer clear, others collide. The pattern follows probability, chaotic in the near term, foreseeable across eons. We're existing in a narrow era where strikes are infrequent enough to allow societies to thrive, yet frequent enough to demand vigilance. The asteroid that wiped out the dinosaurs slammed into Earth 66 million years ago. Measuring 10 kilometers in diameter, moving at 20 kilometers per second, it unleashed power rivaling billions of atomic bombs. The resulting hole spanned 200 kilometers. Ejecta soared into the upper atmosphere. Sunlight dimmed across the planet. An epoch concluded. History could repeat itself, unlikely in the immediate future or within our generation. Still, the real issue is detection. Will we spot it in advance? Will we possess the means to act, having constructed the infrastructure, advanced the tech, prepared the experts, and aligned the organizations for a coordinated effort? Or will we mirror the dinosaurs, oblivious right up to the moment the heavens ignite? R2 won't trigger that catastrophe. It's diminutive, distant, and closely monitored. Yet it serves as an examination. A trial run for our monitoring networks, our information channels, our capacity to face ambiguity with clear-headedness rather than frenzy. To date, we're succeeding. The celestial body is under constant observation. Its path is being fine-tuned. Potential dangers are being relayed transparently. Panic remains absent. It ought to stay that way. Instead, focus on the shortcomings, the overlooked zones, the tracking lapses, the bureaucratic hurdles, the oversights stemming from misguided focus, timing, or equipment. These hold the true value. These deserve priority. Observe the heavens. Advocate for superior scanning tech. Challenge the stories we hear. Remain inquisitive. Maintain doubt. The universe brims with marvels and perils alike. Wonders typically pose no threat to appreciation. Perils, however, don't signal their intent. They skip formalities. They simply manifest. In those instances, what shields us from oblivion is the effectiveness of our early warning setups and the swiftness of our countermeasures. 8 days from perihelion. Our two approaches. Data indicates minimal threat, but data offers no ironclad guarantees. Odds wrapped in formulas can still defy expectations at times. Hence the scrutiny. Hence the computations. Hence the investment in observatories, the education of stargazers, the support for mapping initiatives, and the global partnerships. The flip side is ignorance. And ignorance outstrips the dangers posed by the rocks themselves in peril. Space isn't barren. It's littered with rubble, shards, transients, drifters. The majority glide by without incident. A few don't. R2 underscores that our cosmic locale isn't serene, that orbital congestion is genuine, that peril lingers at a low but persistent level, and that alertness isn't overreaction. It's essential for endurance. Keep your eyes upward.